All right, good morning, everyone. Hope you're all well rested. I slept 10 hours. We'll see if anybody slept more than that. And we've heard yesterday morning from Professor Sriramkumar, who was telling us about primary gravitational waves produced during inflation, and today we're looking forward to hearing more about secondary gravitational waves, so please take it away.
Thank you, Andrew. So we talked about the primary gravitational waves yesterday. I introduced you to inflation and reheating. Both inflation and reheating will play a role in our discussion today as well. And we talked about the primary tensor power spectrum in slow roll inflation. These are the gravitational waves generated from the quantum vacuum. And we talked about constraints on the inflation from the CMB data. And what we essentially learned is that the amplitude of the primary tensor perturbations is constrained to a certain level, and it is usually quantified in terms of the so-called tensor to scalar ratio, and we saw the upper bound is about 0.036 or so, the 10R of 0.036 or so. And you should recognize this upper bound is, constraints on large scales, on the CMB scales, again, scales of about, in terms of wave numbers, 10 power minus 4 megaparsec inverse to about 1 megaparsec inverse or so. And on smaller scales, we saw the amplitude of the primary tensor perturbations can be enhanced due to non-trivial post-inflationary dynamics. And we saw in particular how reheating can give rise to a positive tilt, and in such that, the omega GW that I talked about, the dimensionless spectral density of gravitational waves, can be comparable to the sensitive curves of the various gravitational wave observatories. Today, what we are going to talk about is generation of gravitational waves enhanced by scalar perturbations on small scales. I talked about the constraints on the tensor perturbations. I briefly mentioned how the scalar amplitude is well constrained on large scales. It's often referred to as Kobe or CMB normalization. The scalar amplitude, which I will go to in a minute, I had indicated at some point of time, just bear with me. Here, this scalar amplitude is well constrained. It's like 2 times 10 power minus 9 or so, corresponding to a delta t by t of 10 power minus 5. And that is well constrained. But there are no such constraints on smaller scales. And what we will try to understand today is what happens when you enhance the scalar amplitude or the scalar power on small scales, and what are the consequences, corresponding consequences. I will also narrate the story of why people started discussing these situations where you have enhanced power on small scales. Coming back to my slides, okay, so then I will go on to discuss how such gravitational waves generated by enhanced scalar perturbations can fit the NANO-Grav data very well. And I will close with a brief outlook. So I just need to run through these slides because the laptop is far away. So this is where we were, okay? We finished with a slide such as this. And we need to, of course, turn to scalar perturbations. I had already indicated earlier as to how there are, when you talk about the perturbations in the metric tensor, you can introduce 4 scalar functions, but there are 2 coordinate degrees of freedom that can correspond to scalar. So you are essentially left with 2 independent scalar degrees of freedom. There are 2 ways of studying the scalar perturbations. Remember, in the context of gravitational waves, there was no further gauge choice or coordinate. Considerably simpler, and therefore we are going to work with a particular gauge where we have introduced these scalar functions, which we have referred to as phi and psi, and these are often referred to as the Bardeen potentials. So you have this, line element, FLRW line element, where there are no, remember, at the leading order in perturbation theory, the scalars, tensors evolve independently. We have studied the evolution of the tensor perturbations. Now we are going to, study the evolution of the scalar perturbations. And the scalar two functions that we have introduced to describe the scalar perturbations are phi and psi, and as I already mentioned, they are often referred to as the Bardeen potential. What do you need to do? Well, there are two ways of arriving at the equations of motion governing these scalar perturbations. One is study the, Einstein's equation, turn to the Einstein's equation, or again, as Mohanty discussed, as Subhendra Mohanty discussed yesterday, you can arrive at the second order action. The second order action is more difficult to arrive because you have to go up to the quadratic order in the perturbations. But in contrast, quadratic order in the linear perturbations. But here I just need to calculate all the quantities of interest at the linear order in the perturbations. And I talked about the scalar perturbations in the metric, right? And the decomposition theorem states that you have to equate on the left-hand side, if you have the Einstein's equations, if you have the scalar perturbations, you have to, on the right-hand side, you should have only the scalar perturbations associated with the stress energy tensor. If you take a generic stress energy tensor and you assume that there are no anisotropic stresses, then you can write the stress energy tensor much in the same manner you did with the metric tensor. You can write it in this form. You can, you can have a delta rho, the perturbation in the energy density, which is a scalar, all right? And you can write is, the T0i, delta T0i component as a gradient of some quantity, right? It has to involve a scalar. That can be a vector, but we are not interested in it, okay? And the spatial components will involve the perturbations in the pressure. And once you have the right-hand side, you can calculate the delta G mu nu associated with the metric, and all you need to do is, write the first order and the Einstein's equations, and they are given by these expressions. And the important point to note is that when you look at the I not equal to J components, what they lead to in the absence of anisotropic stresses, these Bardeen potentials become equal. Essentially, you are reduced to studying one equation of motion governing the scalar perturbations. The late-time physicists, large-scale structure guys, for instance, talk about the Bardeen potential. The primordial physicists will often refer to something known as the curvature perturbation, which I will introduce in a couple of slides. Now, how does this, potential, Bardeen potential evolve? It is not very difficult to understand. All you need to do is that you can combine the third equation and the first equation. And remember, we go back and forth between conformal time and cosmic time coordinates. You can write it in terms of the conformal time coordinates. The primes denote differentiation with respect to the conformal time coordinates. And we have introduced a quantity called delta PNA, which is given by this expression. It is what is often referred to as the non-adiabatic pressure perturbation. Okay, and what essentially happens is that if you have a perfect fluid, this is often set to 0, or it has to be specified in some manner, and therefore the right-hand side will be 0 if you have a perfect fluid. Otherwise, this is essentially the Bardeen potential equation governing the Bardeen potential, and for that reason it's called the Bardeen equation. And the Ca squared is what is known as the adiabatic speed of the perturbations. It is essentially P dot by rho dot, or P prime by A prime. And it's a matter of, you have to solve this equation given a background. Given a background, you know P and rho, therefore you know Ca squared, you know script h, and you know everything here, and it's a matter of solving that equation. And there is, I just mentioned a couple of minutes earlier that the primordial physicists talk about a slightly different quantity, not the Bardeen potential, but something called the curvature perturbation. And it is essentially a linear combination of the Bardeen potential and its time derivative. And it is introduced in this manner. And the reason why cosmologists, early universe physicists introduced this quantity will become clear in the next couple of slides. You can take this equation, evidently it's, as I mentioned, it's a linear combination of phi and phi prime. You take a time derivative, and what will happen is that you will have second time derivatives of the Bardeen potential, and you study in Fourier space. Remember, we can study since we are working at the linear order in the perturbations, all the modes evolve independently, and you can arrive at this equation of motion governing the first order equation governing the evolution of this curvature perturbation. Why is it called the curvature perturbation? Well, it so happens, remember, we are working in a spatially flat FLRW universe. What this curvature perturbation essentially reflects is deviation from its flatness, okay? The 3 curvature will be related to this curvature perturbation. So you can differentiate this quantity, use the Bardeen equation, and arrive at this equation governing Rk prime. Now, I mentioned earlier, if you have perfect fluids, delta P and A is 0. And if you are on super Hubble scales, okay, this term goes away when delta P and A is 0. If you are on super Hubble scales, what essentially you are interested in the limit where K is very small, okay, compared to AH. And in such a case, what you have is Rk prime nearly 0 on super Hubble scales. In other words, Rk is a conserved quantity. And what you essentially find is that from the time of, very close to Hubble exit during inflation until the time of re-entry, this Rk is constant, and therefore it is very convenient to define the power spectrum, etc., in terms of this quantity. We wanted to solve the Bardeen equation. And just like we did in the context of, remember, we introduced something called the Mukhanov-Sasaki variable to simplify that equation, second order differential equation that we have here, to essentially get rid of this phi prime term. You can introduce an equivalent quantity. So essentially reduce it to something like a Schrodinger equation and try to see whether you can solve. Okay? And this can be done by introducing this combination. And what you find is that it satisfies a differential equation of this type. Okay? And this happens to be very simple to solve in the following limits, okay? When delta P and A is 0, like in the case of a perfect fluid, we will see what happens when you have scalar fields in a few slides later, okay? So when delta P and A is 0, and on super Hubble scales, what essentially happens is that this doesn't, contribute either. So you're left with a differential equation, which is of the following form. So you have U double prime minus theta double prime by theta U K equal to 0, okay, nearly equal to 0. Evidently, one of the solutions is proportional to theta, okay, and what you find is that, you can write down, so the solution in this limit is easy to obtain. The other solution can be written in terms of integral over theta of this form. And you have certain coefficients, the coefficients will become clear, the nomenclature will become clear in a matter of minutes, okay? And if you now assume power law inflation like radiation or matter domination, and then what you find is that this solution, okay, for phi k has this form, okay? Remember, all this depends on just the background, the scale factor. Once you give me the scale factor, this quantity is well known, can be determined, and therefore this can be arrived at. So the behavior of the Bardeen equation, the solution to the Bardeen equation on large scales is as follows. There are 2 possibilities, and of course it's a second order differential equation. It has 2 constants, and which I've called Cg and Cd. But what essentially happens is as follows. Notice this is a constant, the Bardeen potential. One solution is a constant, and the other solution has some time dependence. But at very early times, this becomes very large. In other words, this decays with time. At early times, it is large, and it is for this reason it's called the decaying mode. And this can survive in the late universe only if the amplitude of the perturbations is very large at very early times. And this is evidently not possible if you are assuming a perturbations about the FLRW universe. So often we set this to 0, and you essentially have this result that phi k is a constant on super Hubble scales. Now, this allows us, this and the fact that, the R itself, the curvature perturbation I introduced in the previous slide is a constant on super Hubble scales, allows us to relate the Bardeen potential at different times. So I had earlier, you remember, R was a combination of this, phi prime is 0, and therefore you can immediately relate the Fourier modes of the curvature perturbation to this quantity Cg. G just essentially means it's a growing mode. I mentioned this is a decaying mode. This is a growing mode. It's not quite growing. It is strictly a constant on super Hubble scales. And that is related to Rk. Remember why we introduced inflation. Essentially, we want what is the initial conditions on these perturbations Cg. Okay, and if you are just studying late time evolution, when the modes are not inside the Hubble radius, all that you will know is that the Bardian potential it behaves in this form, but we do not know what is CG of k, and that is essentially provided by inflation. And coming back to this relation between Rk and phi k, so Rk is essentially given by this expression, all right? And since Rk is conserved, right, on super-Hubble scale, and phi k is a constant on super-Hubble scales and power law expansion, you can arrive at this following. Using the conservation of Rk, you can relate the phi k during radiation domination to the primordial CG of k in this manner. That is why you see often factors of 2 by 3 when you go from inflation to radiation domination. And there is a 3 by 5 relation between the primordial perturbations. If you're talking about modes which re-enter during matter domination, there is a factor of 3 by 5, and which corresponds to all I have made use of is the fact that WR is 1/3 and WM is 0. And it is interesting to note, you can now try to relate phi km using CG of k and phi r, and they have a factor of 9 by 10. This is the well-known result that on large scales, the amplitude of the Bardian potential does not change much with time. This is all about late-time evolution, post-inflationary evolution of the scalar perturbations. And what happens, how do you generate these perturbations? We talked about the generation of the tensor perturbations from the quantum vacuum. How do you generate the scalar perturbations? Well, essentially, it happens in the same manner. So now we are in the epoch of inflation. We are assuming for simplicity, inflation is driven by a single canonical scalar field. And let delta phi, we had a phi which denoted the background evolution. We discussed different possible evolution, different solutions, etc. And let delta phi denote the perturbations in the scalar field. Remember, we are working in the longitudinal gauge. I had introduced the metric earlier, and there was a Bardian potentials, phi and psi. But we've seen that, if there is no anisotropic stress, which is true in the case of a scalar field, you can show that delta Tij for a scalar field in a FLRW background is proportional to delta Ij. There is no non-zero I not equal to j component, which essentially implies, again, even during inflation, phi equal to psi, just as in the context of matter and radiation domination. And this delta, that phi is, we have set phi equal to psi, and therefore everything can be expressed in terms of delta phi, the background field phi, and capital phi. And what you can do is that, you can plug this in the Einstein's equations. Now what we have is, a relation, and specific expressions for delta rho and delta p, and you can plug those expressions in the first order Einstein's equation that we had, and you can arrive at the Bardian potential. And what you find is that the delta PNA that we had, which we didn't, it has to be specified for the case of fluids, has a specific form here. Okay, and one of the important points to note is that, remember, earlier when we looked at the conservation of the curvature perturbation, there were two terms, one which was proportional to k squared phi and delta PNA. In the case of fluids, we didn't know what delta PNA was. We can set it to 0 if you have a perfect fluid, or if you have a more complicated fluid, you have to specify the form of delta PNA by hand, depending on the microphysics of the fluid. But in the context of scalar field, what you find is that this term also behaves like this term. Okay, so both of them are proportional to k squared. And if you recall, what we did was that, on super-Hubble scales, we said this term is very small, and therefore Rk is conserved, provided delta PNA is 0 in the case of fluids. In the case of scalars, what you essentially find is that delta PNA is also proportional to k squared phi k, in Fourier space, and therefore you can, the Rk will be conserved on super-Hubble scales during inflation. Okay, and so what do we have? So we had made use of this relation. Okay, we have made use of these equations here, and what you find is that during inflation, right? The first order equation, all I just mentioned is that, we have an expression for delta PNA. We plug in this expression for R prime, and therefore you arrive at this extremely simple relation for Rk, the curvature perturbation during inflation. And what you do is that you differentiate it one more, okay, and use the background equation. It has this simple form. Notice we had arrived at a similar equation for the tensor perturbations gamma ij. You had gamma ij, double prime, plus 2a prime by a, there was no z, a prime by a, and there was r prime, gamma ij prime plus k squared gamma ij equal to 0. There is a very close resemblance between the equation of motion governing the curvature perturbation and the tensor perturbations, primary gravitational waves, and this quantity z is given by this expression. Now you may wonder, where is the inflationary model and the different spectra in the inflationary model comes in. These are all buried in this quantity z. Given an inflationary model, that is what a v of phi, I need to solve for phi, I need to solve for a, I need to obtain h, and plug in this expression and solve for the curvature perturbation, evolution of the curvature perturbation. So you can quantize the curvature perturbations much in the same manner as you quantize the tensor perturbations. And what you do is that you elevate the classical quantity script r to a quantum operator, and you can Fourier decompose in terms of creation and annihilation operators, and in the same manner as you did in the case of tensor perturbations, and they satisfy the standard commutation relations, and these Fourier modes fk satisfy this equation of motion. Remember, we had something called gk in the context of tensors. We have something called fk, which have a very similar equation in the context of scalars. And you can define a curvature perturbation spectrum, which is often referred to as a scalar power spectrum, in this manner, all right? And if you take this expression here, the Fourier decomposition of the operator R in this, and plug it in this expression and evaluate in a vacuum state, this is the Bunch-Davies vacuum associated with the scalars, okay? And it is defined through this relation, you arrive at this expression. So all you need to do in the context of tensor perturbations is that, I don't think I have repeated the slide here. Remember, you are, at very early stage during inflation, you are well inside the Hubble radius, and you impose those initial conditions at those times, and you evolve the spectrum at late times. I'll come back, and I need to run back a few slides. I'll come back and show it after the next slide. So, as in the context of tensor perturbation, you can introduce something called a Mukhanov-Sasaki variable. This is called the scalar Mukhanov-Sasaki variable. Remember, in the context of tensors, gk was apart from factors of √2 by MPL, there was an expression like uk by a. And by the way, the √2 by MPL arises for the reason that Subhendra Mohanty talked about. When he wrote the expression for the action for the tensor perturbations, you had a 1/32 pi g factor. To absorb that, you need to introduce this √2 by MPL, and that carries everywhere in the tensor perturbation spectrum, and that is responsible for ensuring that the tensor power spectrum we define is dimensionless. So let's come back to the scalar Mukhanov-Sasaki variable. It's not surprising that you will arrive at an equation. This should be Z, not A. That's a typo. So you are essentially have a time-independent oscillator equation. Time-dependent oscillator equation, which is now the time dependence is determined by Z double prime by Z instead of A double prime by A. And you can plug this decomposition, plug this relation in to obtain this relation for the scalar power spectrum. As in the case of tensors, you introduce, you impose the initial conditions, the so-called Bunch-Davies initial conditions in the sub-Hubble limit when the modes are well inside the Hubble radius. So let me just go back to just, remind you what I had in mind. I need to go quite a few slides here. Okay, so you are imposing the initial conditions. Remember, in the case of tensors, you impose these Bunch-Davies initial conditions because, at very early times, the modes are well inside the Hubble radius. They don't feel the curvature of space-time. They behave like Minkowski modes, and you impose these perturbations, initial conditions on the perturbations and evolve them. And what you find is that, as I indicated, they oscillate in the sub-Hubble regime, and soon after they leave the Hubble radius, for this mode, they leave at e-fold of 18 or so, and the amplitude freezes. So you can evaluate the scalar power spectrum in the sub-Hubble limit. In the super-Hubble limit. Just let me go back. So that's it. Now we want to calculate the power spectrum in slow roll inflation before we start discussing how to enhance power on small scales. So what you can do is that you take the expression. Remember, Z was A phi dot by H, I've already introduced the slow roll parameters. With a bit of algebra, you can arrive at this expression. And you can also, in the first order, this is exact, I should emphasize. And at the leading order in the slow roll parameters, you can arrive at this relation. This is something we had used in the case of tensors as well. Then what you can do is that you can show that z double prime by z is given by this expression. And as I already indicated, if your z double prime by z or a double prime by a is 1 over eta squared, the solutions are Hankel functions. And it's a matter of determining what this, index of the Hankel function is, and you choose amongst the two solutions to this differential equation. There is this Hankel function and its complex conjugate, which is h nu 2. You need to choose one which satisfies this initial condition at early times, and that picks your solution, which is the first Hankel function of the first kind. And the nu s is given by this expression. What do you do? As I indicated earlier in that figure, you impose the initial conditions at early times and you evolve them to sufficiently late times, and you evaluate the spectrum in super-Hubble limit. And we had a similar expression for the case of tensors earlier. You can arrive at a similar, the corresponding expression for the scalar power spectrum, and it is of this form. These are all constant, and what you are interested in the scalar spectral index, you know this amplitude, okay? In the case of tensors, if you remember, the amplitude was h squared by mpl squared. So it just depends on the scale of inflation. That is why, people are after detecting the imprints of the primary tensor perturbations, because you know what the scale of inflation is. But in contrast, this amplitude of the scalar perturbations contains this factor of 1 over epsilon 1. And the other point we are interested in is the scalar spectral index, ns minus 1. It is defined slightly differently from the case of scalars. And what you can read off this, ns happens to be this. And what you find is that ns is, okay, I'm a little concerned about this. I think it is fine, okay? ns, as we had seen, is of the order of 0.96 or so. That is what the CMB observations suggest, okay? So now, when we arrive at this spectrum, right, what we have assumed is that inflation is of the slow roll type through the entire period. Remember that figure that I had in the case of the Sriramkumar model, where there was a field nicely rolling down the potential, and the first slow roll parameter, I did not indicate. There will be other opportunities for me to illustrate the behavior of the first slow roll parameter. What essentially happens is that it remains small. Maybe I can indicate here. So in most of slow roll models, what happens is that the first slow roll parameter is small, and it slowly grows, and it crosses unity, suggesting end of inflation. So this is NN. What I'm plotting is the behavior of the first slow roll parameter as a function of e-folds. It starts at some value, maybe 10 power minus 2, 10 power minus 3, depending on your model at hand, and it crosses unity, and this is where inflation ends. Okay? Now, in such a case, this spectrum is valid for all the scales. Let me plot this picture here rather than change slides. Remember, you have this epoch of inflation, slow roll inflation, and what I am plotting is this is the end of inflation, this is radiation domination, okay? This is inflation, and modes are leaving the Hubble radius, okay? And this is this last mode which leaves the Hubble radius, okay? And this is your K star, okay? This is where, I'm sorry, this is K star, this is K star, okay? And this leaves about, something like 50 to 60 e-fold. This is N star. Okay, all right. What you find is that if you have slow roll inflation, the power spectrum is red. Okay, let me, what have I plotted here? Log of lambda p and log of the Hubble scale, right? And as a function of log a, right? If you plot the scalar power spectrum, what you find is that it is Ps of k, okay? It has a red tilt, okay? I have exaggerated the tilt. Right? You have, from scales of about 10 power minus 4 to virtually the end of inflation, which can be something like 10 power 19 megaparsec inverse. So this is something like, the spectrum is something like k power 0.96. What is it? I'm sorry, k power minus something like 0.04. Okay, a slight red tilt, and this amplitude is roughly 2 times 10 power minus 9. Okay. That's what the power spectrum in slow roll inflation looks like. That's what this is, okay? From the largest scale to scales that leave the Hubble radius at the end of inflation. Now, but we have the constraints from the CMB only over large scales, or scales from 10 power minus 4 to something like 1 megaparsec inverse or so. Okay, this is what the CMB constraints. There are no such constraints. We don't need to have power spectrum of this type on smaller scales. And we can understand what happens when we try to enhance power on small scales. But why do you want to enhance power on small scales? And there is a side story here. I'm sure you have seen this picture, all right? This is the so-called LIGO binary black holes. And what people found is that, naively, I presume people thought that the masses of the black holes, these astrophysical black holes, will be of the order of a few solar masses, maybe 10 solar masses. But LIGO has picked up these black holes, which are rather heavy, of the order of tens of even 100 or 200 solar masses. And the question is whether these black holes could have formed in the early universe rather than at late times due to astrophysical phenomena. I've been talking about how modes re-enter the Hubble radius, right? Now, what I will discuss is that if you want to form these black holes, the power on the scales when the modes re-enter the Hubble radius should be significantly higher in order to form those black holes. And that is what I have indicated. Why is this not changing? Yeah, there it is. So this is again a picture, slightly different picture, but we have seen this picture. What has been plotted is the co-moving scale. Here I have plotted the physical scales. Here is the co-moving scale. The wave numbers correspond to constant values. So this is the CMB scales. This is the physical scale where the CMB scales leaves at very early time. A much smaller scales leaves at much later time. And that is what it is here. This is the Hubble radius, co-moving Hubble radius. Remember, it has a slope of -1 and during inflation, and it has a slope of +1 during radiation domination. These modes leave the Hubble radius and they re-enter at later times. And these correspond to the CMB scales, and these correspond to much smaller scales. Now, if you want to have significant number of black holes formed, if you only have slow roll inflation, power spectrum as in slow roll inflation, with an amplitude of 10 power minus 9 or so, you cannot form enough number of black holes. You need to enhance power on these small scales which re-enter at late times in order to form a significant number of black holes. And how do you, in other words, what you need is as follows. This is something like RK instead of the power spectrum. And I indicated that power spectrum is like 10 power minus 9. You take the square root or so, it is like somewhere between 10 power minus 5 and 10 power minus 4. This is the amplitude of the primordial curvature perturbation in dimensionless units, okay, on CMB scales, on the large scales of about 10 power minus 4 to about 1 megaparsec inverse. If you want to produce enough number of black holes, this should be close to order 1 or 0.1 or so. And in other words, if you have only slow roll inflation from the start to the end, you will not be able to form enough number of black holes, and they will not be able to explain the LIGO black holes, the black holes that LIGO has seen. And so what you need is power spectrum, which starts here, but rises to these values and takes a peak here, has a peak here, substantial peak here, before it falls down due to the evolution of the scalar field at late times. That will become clear as we proceed. Now, how do you achieve that? Okay, if you want a strong feature in the primordial power spectrum. You don't want a featureless spectrum which is nearly scale invariant. You will not produce enough number of black holes, and as we will see, such scenarios will not produce enough amount of secondary gravitational waves as well. That will become clear towards the end of our discussion. So you want a spectrum that starts here, rises to these values. And this is achieved if you have deviations from slow roll inflation. You need a breakdown in slow roll evolution. And this, such deviations in slow roll inflation lead to specific features. And if you want a sharp rise, you need a particular type of deviation from slow roll inflation. You need, you would have heard this term, an epoch of ultra slow roll inflation. I talked about slow roll inflation, where the first slow roll parameter I have indicated here, it is very small, it rises, and crosses unity, leading to the end of inflation. If you want an, sharp rise in power, you need an epoch of ultra-slow roll inflation where the first slow roll parameter is exceptionally small. How do you achieve this ultra-slow roll inflation? Let's turn to this equation of motion governing the scalar field. We have seen this equation at early times. Consider a situation where V phi is 0. You have a potential which contains, say, a point of inflection. So at the point of inflection, V phi is 0, and near the point of inflection, V phi is rather small. So around these regimes, I can ignore this term, and therefore I can immediately integrate this term. So what do you have here? You have phi double dot is essentially is minus 3h phi dot, when V phi is 0. And remember, this is A dot by A. So which is phi double dot by phi dot is minus 3 A dot by A, which can be immediately integrated to obtain phi squared phi is proportional to A minus 3. So if you have a point of inflection in the potential, and as the field crosses the point of inflection, phi dot will behave in this manner. And the first slow roll parameter, which we had introduced, can be written in terms of phi dot in this manner. Imagine a scenario, you have slow roll inflation, the Hubble parameter is roughly a constant, and therefore this h is a constant, and therefore phi dot squared essentially behaves as a power minus 6. How do you know epsilon is very small? It is growing smaller and smaller. If you start with small value of epsilon 1, it is growing smaller as it hits a point of inflection in the potential. Okay, how do you know it? The slow roll conditions are violated? Well, you calculate the second slow roll parameter, which is straightforward to calculate, and it happens to be minus 6 or so. So if you have a point of inflection in your potential, you can have a situation where there is a strong departure from slow roll, and as we will see, such scenarios can help us raise the amplitude of the scalar power spectrum over modes which leave the Hubble radius just prior to or during this epoch of ultra-slow roll inflation. So here is a specific model that that contains a point of inflection. Okay, there are a couple of models. There are many models in the literature, and here is an example of the behavior of the first 2 or 3 slow roll parameters. And here is where it is better for me to show this. Okay, remember the picture of the inflationary attractor. So what you have is the phi dot or phi d phi by dn, and you have the scalar field behaving, all merging towards the attractor. I haven't shown that, but I mentioned. Okay, and it remains on the attractor until the termination of inflation. But there is some difference when you have an epoch of ultra slow roll inflation, when you have deviations from slow roll. So firstly, let us focus on the behavior of this to compare with the earlier figure that I had. This is what essentially slow roll inflation does. Okay, there is an attractor, and here very clearly, okay, all the trajectories merge towards this curve. But there is a point, this is the point of inflection. At the point of inflection, notice what happens. The velocity of the field here is extremely small. The point of inflection slows down the field tremendously, okay? But somehow, the field may get stuck, but if you choose your parameters carefully, it will not get stuck, but it will emerge from this point of inflection, and you have inflation ending somewhere here. And this is the slow roll solution. The dotted line is the slow roll solution. The slow roll attractor, it is falling on the trajectory, is falling on the slow roll attractor at early times. But here is the departure from slow roll inflation. And what essentially happens is that the field value, velocity value of the velocity of the field or the speed of the field becomes extremely small, and it comes out again, leading to the end of inflation. And these are reflected in the behavior of the slow roll parameters. I've plotted the first slow roll parameter and the second slow roll parameter. I will ignore this. We don't need to worry about that. Okay, so what essentially happens is that, notice, there is an epsilon 1 behaving in this manner. It's slowly rising, much in the manner that you will have in slow roll inflation. But suddenly, as it hits the point of inflection, suddenly there is a rise and there is a rapid fall. And this fall can be like a power minus 6 or something, close to minus 6, depending on the model at hand, depending on the details of the model. There is a sharp fall, and then it rises again. It comes here, it rises again, and it crosses unity, leading to an end of inflation. And epsilon 2 remains very small at early times. Okay, and suddenly it becomes large. There are different models. It has been plotted, the dotted and the dashed lines. I'm sorry, the solid and the dashed lines. And this epsilon 2 during this epoch of ultra slow roll is of the order of -6, -7 or so. And how do we calculate the power spectrum in such situations? It's not very difficult to do. There is a nice paper by Burns and others which helps us understand the shape of the power spectrum in such models which permit a period of ultra slow roll. I hope you understand what I'm talking about. You have slow roll inflation. There is a deviation from slow roll. There is an epoch of ultra slow roll inflation. And then in some sense, there is a rise in epsilon 1, which leads to an end of inflation. So let's model this analytically. So you have three epochs. The first epoch during which up to a certain times from some initial stage of inflation to eta 1 when the slow roll parameter is extremely small. And there is a period where the slow roll parameter decreases rapidly, like a power -6, in this case that I talked about, when fields cross a point of inflection in the potential. And then I need to make this grow. I need to make this grow leading to an end of inflation. So I've chosen a positive power of A. From some value, it rises, lead to an end of inflation. And, the behavior is exactly like what you have. I just have made it constant instead of a small rise. It's a constant, it falls rapidly and rises, leading to an end of inflation. And as we discussed, what you have is that, you have epsilon 2 is nearly 0 during the initial stage of slow roll, and it is -6, suggesting ultra slow roll. And during this late time, when epsilon 1 is rising, different models, these different models will lead to different ways in which this rises, and I have chosen for analytical purposes to work with 2, and that reason will become clear very soon. And so, as I mentioned, there is a period of ultra slow roll inflation which follows an epoch of slow roll inflation before epsilon 1 rises, leading to the end of inflation. And the fact that these numbers are large imply you have deviations from slow roll inflation. What you can show amazingly is the following. You can take these expressions for the slow roll parameter, and since you can choose your parameters here, epsilon 1i, epsilon 1a, to be very small, so that the background evolution as far as the scale factor is concerned is very similar to that of d zeta. Under these conditions, what is amazing is that in d zeta inflation, okay, I will just go to that slide, just bear with me. Remember, z double prime by z was given by this expression, okay? What happens is that, if you assume this is small and you throw this away as well, which you can do to get the leading, nearly scale invariant spectrum, or scalar power spectrum, okay, then what happens is that this behaves like 2 by eta squared. What you can show is that in all this, in ultra slow roll inflation as well, during ultra slow roll inflation as well, when epsilon 2 is -6, it is 2 by eta squared. In other words, if you recall, in the case of tensors, a double prime by a was 2 by eta squared, and then in the d zeta, we had an extremely simple expression for the Mukhanov-Sasaki variable. So in these two phases, it is just 2 by eta squared, so you immediately know the solution. And I've chosen 2 so that I can solve this exactly as well. Remember, these are all solutions can be expressed in terms of Henkel functions. I'm choosing the indices of the Henkel function so that I can write it in terms of some simple, extremely simple functions. And the solutions are as follows. You have 3 regimes. The first regime where you have the d zeta modes that I talked about in the case of tensors. And in the second regime, remember, z double prime by z is 2 by eta squared. And therefore, the solutions are the same. But because there is a transition, I need to write them in terms of linear combinations. There is a subtle point. What happens is that this z double prime by z has some delta functions at these transitions. You need to account for them. If you have done quantum mechanics with a Dirac delta function, you know how to attend to these Dirac delta functions. You need to impose those conditions carefully on the derivative, time derivative of the mode functions, and you can determine these coefficients. I mentioned in the first 2 regimes, it is very similar to d zeta. In the third regime, I've chosen such that I think instead of Henkel 3 by 2, I've chosen Henkel 5 by 2. So the solutions are of this form. And you can match and arrive at these coefficients. The coefficients are fairly lengthy and they are not particularly instructive, okay? So I have gone ahead and plotted the power spectrum. So what I have done is that, I have numerical, analytical results, okay, which appear in blue. And I have also modeled it, tried to model it numerically and compared the background evolution as well as the results for the power spectrum. So what do you have? You have an epsilon1, which is constant, comes down, rises. Okay, and in the context of numerics, they don't match exactly because I need to model it and there are a few parameters involved. This to illustrate the broad behavior of both the background and the power spectrum. And epsilon2, as I mentioned, there is a constant for a period of time where epsilon2 is close to -6 or so during the epoch of ultra-slow roll, and then it vanishes thereafter. Oh, sorry, it becomes 2 thereafter, okay? And we will not worry about epsilon3. It is important if you want to calculate quantities like non-gaussianities in these models. And what you have is this power spectrum. One of them is the red one, and the other, one of them, the red is the numerical one, and the other is blue. There is some issue with the amplitude depending on the matching of the parameters in the analytical expressions and the numerical expression. But the shape of the spectrum is very clear. These cyan part corresponds to modes that leave the Hubble radius during an epoch of ultra-slow roll. In this particular example, what happens is that the peak is very flat. Okay, it depends on the duration of ultra-slow roll that you have. You have a nearly scale invariant spectrum, and this has not been properly normalized. Okay, this has to be Kobe normalized. These are the modes that leave the Hubble radius at very early times. So the amplitude and NS and the tensor to scalar ratio has to be consistent with the CMB data. But on smaller scales, there are no constraints. There are some constraints on intermediate scales, which I will talk about in a few slides later. And then there is a rise in power, where you can have a situation where the power is, significantly larger what you have on large scales. And then, there is a fall. This arises because of the fact that you have, this rise in epsilon1 at late times, leading to the end of inflation. So you have power spectra, which is flat, and we can, this growth, it can be shown. This was shown by this, as I mentioned, in this paper by Burns, Cole, and Patel. And you can show this rises like k power 4. There is a peak in this particular model. It falls like k power -2. And you can construct, this is how roughly you can understand analytically what's the shape of the power spectrum in ultra-slow roll inflation is. And, I earlier talked about a particular models of ultra-slow roll inflation. There are a subclass of models where what happens is that, as epsilon1, notice before it starts falling, it rises. In some subclass of models, epsilon1 crosses unity, before it falls down, and these we refer to as punctuated inflation. But otherwise, the behavior is very similar. You have we have a nearly flat region, slow roll region. There is an epoch of ultra slow roll before epsilon1 rises, leading to the end of inflation. And how does the power spectrum behave? These are the curves in red and dash in red are the scalar power spectra, and the ones in blue are the tensor power spectra. These are from some class of ultra slow roll models. These are some class of punctuated inflationary models. Notice, focus on these models, focus on these power spectra. You have a nearly scale invariant spectrum, and there's a sharp dip. In fact, you can show that there is a dip which will arise both in 2-point functions and all the higher order correlations. There is a rise which behaves like k power 4, and there is a peak, depending on the parameters of the potential, and there is a fall in the power spectrum in all these cases. So now we need to understand the tensor perturbations at the second order. I'm not going to discuss the formation of PBHs. I mentioned them to motivate why we need enhanced power spectra on small scales. And I'm going to just quickly turn to the calculation of what are known as secondary, the dimensionless spectral energy density of secondary gravitational waves. And I think Professor Tasinato in one of the lectures, in some of the lectures later, will discuss the formation of PBHs. And there, I'm sure he will consider spectra like this and go on to estimate how, show how higher number of black holes are formed if you have departures from slow roll inflation and you have peaks in power spectra on small scales. So let's turn to the secondary gravitational waves. The derivation is actually fairly lengthy, and I'm not able to provide all the arguments. So I'm just, at some point of time, I have to wave my hands and indicate the form of the source that generates these secondary gravitational waves. But the spirit in which this calculation is done is not very difficult to understand. So what you have is that you need to introduce second order perturbations. What are secondary gravitational waves? I mentioned they are induced by scalar perturbations. There are other possibilities as well. You can have secondary gravitational waves induced by magnetic fields during inflation or post-inflation as well. Okay, so what you need to do is that you need to set up perturbation theory at a higher order. There is another point I had mentioned. At the linear order in perturbation theory, there is this decomposition theorem that states that scalars, tensors, and vectors evolve independently, but not so at the higher orders. Essentially, what you find is the second order metric perturbation that we have introduced here. We have ignored the first order vectors and the first order tensor perturbations. We have introduced the second order metric perturbations, and we have introduced scalar and vector perturbations at the first and the second order. And what you essentially find, what you need to do is that you need to write the equations at the first order, and you need to, arrive at the equations at the second order. You need to use the equations at the first order in the second order equations to arrive at the equations of motion governing this Hij. Fairly lengthy algebra, but this is well explained in this classic paper by Bauman et al. And I would urge you to take a look at this paper. It will involve some derivation. So what you arrive at is as follows. So I mentioned as to how these are tensor perturbations that are sourced by scalar perturbations. The quantization, you don't need to quantize them. These are classical, right? This Hk is classical. So the equation of motion for each of the Fourier modes, you can decompose, that's what I wanted to say, the Hij in terms of the polarization tensor and the modes. Instead of Gk, I have called them Hk. In contrast to G subscript K wave number, you have a G subscript K vector because the source contains the wave vector as well. Okay, and remember, in the case of primary tensor perturbation, the source was not present, 0. Okay, and therefore that depends only on the wave number. Here it depends on the wave vector too. And otherwise, the structure of the left-hand side is the same. And I've been repeatedly mentioning as to how this tensor perturbations are sourced by the scalar perturbations, and these scalar perturbations are described by these Bardian potential. These are Fourier Fourier modes of this quantity phi1 or psi1. At the leading order, remember, if there are no anisotropic sources, phi1 equal to psi1, only that quantity appears here. Okay, so all you need to do is that, evaluate this quantity Sk of lambda at a given epoch. We will focus on the radiation dominated epoch, okay? And you need to know what these phi k and phi p are during that epoch and up a solution to this Hk. How do you obtain phi k? Well, I talked about how you can solve the Bardian equation, right? And you can determine what the solution to the Bardian equation is. We are interested in this situation where this scalar secondary gravitational waves are generated during radiation dominated epoch. In other words, for simplicity, we are going to assume a scenario where inflation is followed by epoch of radiation domination. There has been instantaneous reheating, and all the modes of interest, small scales of interest, let us say 10 power 4 megaparsec inverse or larger, have re-entered during the epoch of radiation domination. In such a situation, all these phi p are related to the primordial curvature perturbation I talked about through this something called the transfer function, which you can arrive at by solving the Bardian equation. And then you take that guy, okay, take these transfer functions and plug it in these expressions for phi p and phi k minus p, and you arrive at a messy expression like this. Okay, and this is messy but relatively straightforward algebra. Okay, so you need to substitute these transfer functions from the earlier slide into these. This involves derivative. This notation implies this is differential with respect to the argument, and you can calculate what this is, and these are known. Okay, this is a classic paper by Corey and Tirada, where you have these expressions for IC and IS. Okay, so what do? You take these expressions and substitute in these expressions, so you have Hk. But you want the power spectrum of the tensors, which will involve products of these quantities, Okay, so you construct that much in the same manner that you did with the primary tensor power spectrum. And you plug, what you find is that this pH of K is given by this expression here. Okay, and I have already indicated how these quantities IC and IS are. What is the structure of these equations? Now remember, as I mentioned in the context of primary gravitational waves, if you are interested in scales which are much larger than 10 power 4 megaparsec, much larger than KEQ, okay, 10 power 4 megaparsec inverse, or much larger than KEQ, they are well inside the Hubble radius at early times. And that is what causes these oscillations here. The modes are well inside the Hubble radius, and that leads to oscillations in the power spectrum. For simplicity, we can average over those oscillations, and you arrive at this expression. And you can talk about the spectral energy density of gravitational waves, which is roughly modulo factors proportional to the power spectrum here, the average power spectrum, and it is given by this expression. Okay, and you want to construct the dimensionless spectral energy density of secondary gravitational waves. That is not difficult to construct. That is given by this. So it's essentially given by this expression here, where pH of K is given by this. Okay, there is something I have not highlighted. Remember, the HK contains products of Bardeen potentials. Okay, and the Bardeen potentials are in turn will contain products of Bardeen potentials will contain products of the curvature perturbation. And the products of curvature perturbation, when you evaluate this expectation value, will involve products of the power spectrum. There will be 4 RK, right? Each HK contains 2 phi K, all right? So this will contain 4 RK, and when you evaluate the expectation value, you are essentially assuming that these RKs are Gaussian random variables, and therefore you are using Wick's theorem to write this 4-point function in terms of 2-point functions, which essentially involves modulo and overall factor, which has been absorbed here, has been written as products of the curvature perturbation. This PS is essentially the primordial curvature perturbation. So you give me a PS of K, I need to plug this in, calculate this pH of K, and plug in this expression here to obtain omega GW. And as we have already seen, once you know omega GW of K eta, you can calculate the spectral energy density of gravitational wave. Today's you can express in terms of the dimensionless spectral energy density of radiation. So that's all there is, where these IC and IS are given by those expressions that I had shown earlier. There is one case for which you can evaluate this exactly, very easily, is for the case where PS is a Dirac delta function. And those expressions appear, I think, in Espinosa's paper, okay? And I would urge you to take a look at it. I was going to introduce that expression, but I could not do so for want of time. So now what do? You take a power spectrum, like in the case of ultra-slow inflation that I had shown earlier. I thought I had drawn it here, okay? And plug in this expression and calculate this quantity, and plug in this to arrive at the spectrum of secondary gravitational waves. That's all there is to it, okay? And this is the spectrum of secondary gravitational waves. I had earlier shown, let me just go a few slides back. I had shown these spectra here, right? Some of these spectra which go up and come down, and these are the secondary gravitational waves generated during the epoch of radiation domination, okay? You can have, depending on where the peak is located, which again depends on the parameters of the model that you're considering, you can have different peaks in the, or even a wider peak, okay, in the secondary spectrum of dimensionless spectral energy density of secondary gravitational waves. There are a couple of other points I want to mention. Remember what you had in the context of slow roll inflation, okay? Yes, the primary tensor power spectrum in slow roll inflation. If you had slow roll inflation followed by radiation domination, like we are discussing here, I want to emphasize, I want to point out where the primary spectrum will lie in this figure. Notice, if you had only slow roll inflation, this is like 10 power minus 23 or so. Okay, this is where it will be. The power spectrum, the omega GW of secondary gravitational waves will lie here at 10 power minus 23 or so. Remember where it was, where the primary spectrum was. It was a thing at 10 power minus 17 or so. It is worth going back. I'm sorry about this. There it is, right? It was somewhere here. Okay, think of the scale invariant situation which you will have if you have inflation followed by radiation domination. It is at 10 power minus 17. The secondary tensor power spectrum is, is like 10 power minus 23, and that is what you would have if you did not introduce an epoch of ultra-slow inflation. But because you have introduced an epoch of ultra-slow inflation, which led to a rise in the scalar power, that has reflected in this rise in the secondary gravitational waves. And as you can easily see, some of those scenarios can be, either observed by the gravitational wave observatory or at the most constrained by them. Until now, we have talked about the generation of secondary gravitational waves during the epoch of radiation domination. That is, we have assumed instantaneous reheating and assume that instantaneous reheating, and therefore all the modes re-enter during the epoch of radiation domination. But what happens if you have modes re-entering, some of them re-entering during the epoch of reheating, and some of them entering during the epoch of radiation domination? And why is this relevant? This is because of the NANO-Grav data. I'm sure you have heard about this story. I think Ghulam will speak about it, just very soon after my talk. Okay, and pulsars. You know about pulsars and how the PTA has seen a NANO-Grav. a stochastic gravitational wave background, and there is this famous Hellingsdown curve which tells you that it is stochastic in nature, it's isotropic and stochastic in nature, and this curve, expected curve, seems to fit the data reasonably well. I'm sure he will talk about possible deviations from it and whether it is a stochastic wave, gravitational wave background. You can assume a simple shape, amplitude and shape for this gravitational wave background, okay, and try to see whether it fits the data fairly well. And they suggest indeed a certain amplitude and a certain spectral index for this gravitational wave background. And what has been indicated here is that one which is suggested by what are known as merging of supermassive binary black holes. You have, I talked about how LIGO has observed gravitational waves from merging binary black holes, okay? But if you have supermassive black holes, they will be emitting gravitational waves in the domain in the region of frequencies, in the domain of frequencies that the PTA are sensitive to, which are around the nanohertz region. And this is where it, this is what the index should be from these models. There are some details which I'm sort of pushing aside as far as these modeling is concerned. Okay, we are assuming the simplest case, and they don't seem to fit the NANO-Grav data fairly well. What are the other possibilities? The NANO-Grav collaboration has considered different possibilities, and one of the things that fits the data fairly well is something known as SIGW Ghosh. SIGW stands for secondary induced gravitational waves. And remember, my power spectrum had this rise and a fall, and often for simplicity, if you just want to focus on, not focus on the generation, but focus on the impact on the observables, people assume typically a log normal distribution for the power spectrum, and that's what is referred to as Ghosh, and that fits the data remarkably well. But when compared to this astrophysical model involving mergers of supermassive binary black holes. So what did we do? Well, we did the following. There is some other story that I need to mention before I start discussing this. The reason we studied was as follows. People had carried out exercise similar to what we have done earlier, but what had happened was that if you try to fit the data with a peak in the scalar power spectrum, remember we are talking about ultra-slow inflation, where you have a brief epoch of ultra-slow inflation, you have a scale invariant spectrum on large scales, and you have a rise, or k power 4 rise towards the peak, and thereafter, after the peak, it falls down, like k minus 2 or so. When people try to fit only with the PTA data, they ended up with a parameter space where the PBHs were overproduced. The number of PBHs, FPBHs, which has to be less than unity, were greater than 1. Okay, I will illustrate that in one of the slides later. And our job was, our goal was to examine whether you can ensure that PBHs is less than 1. In fact, they are consistent with the observational constraint, and you can fit the data fairly well. And that's our goal. There are some uncertainties in calculating the extent of FPBHs. I believe Professor Tasinato may touch upon it. Okay, and one of the uncertainties is what is so known as the critical value, critical density for the formation of black holes. And I will not discuss this in detail. I'll just say that since we do not know the formation, very well the estimation of the number of black holes formed, so often, there are various methods adopted, and they can lead to slightly different results. To capture these uncertainties, what we are going to do is that we are going to vary this delta C to be, so that they are consistent with the PTA data, and also the fact that, FPBH are consistent with the observational bounds. So we consider different models. It's not difficult to understand these models. What we are going to assume is that some of the modes re-enter during the epoch of reheating, which means that all that analysis I talked about, where you had inflation followed by radiation domination, has to be repeated for a scenario where you have inflation followed by epoch of reheating and radiation domination. Some modes would have re-entered during these different epochs as well. And, would have entered one epoch, and you need to examine their evolution in the second epoch as well. And so we have this reheating parameter, equation of state during reheating. We have this N0. Remember, N0 indicates how the power spectrum falls after the peak, okay? And A0 is the amplitude of the power spectrum at the peak, and, K peak is the location of the peak. And we carried out a run, and you get with just the PTA data, and we found that it was not sensitive to N0, okay? And therefore we threw that out. And then what we did was that, we ensured that it is consistent, our model is consistent whenever we calculate the omega GW as well as FPBH simultaneously, and ensure it is consistent with FPBH less than 1. And we changed the value of the delta C that I indicated. And we also said, we will not worry about this FPBH less than 1. We will actually ensure that it is consistent with the observational constraints as well. There is something I did not mention. There is, you can calculate the omega GW fairly well, if you have modes re-entering during radiation domination or during reheating. But it is a little bit of a challenge to calculate around the domain where the modes are re-entering during the transition from this epoch of reheating to radiation domination. In order to avoid the challenges with those, what we did was that we assumed a rather low reheating temperature of about 50 MeV or so, and that is what I have indicated, okay? So that most of the modes around the domain of which the NANO-Grav is sensitive to have entered in our model, in our scenario, during the epoch of reheating. And these are the assumptions, and what we arrive at, these are the best fit, the posterior probabilities, okay? And what you essentially find, you can focus on this figure. This is for the final model, which is consistent with the PTA data as well as consistent with the constraints on PBHs, okay, on the number of PBHs. And what you essentially find is the following. You find that a higher value of delta C is favored, okay? And what you also find is that, a higher value of WRE is favored. And the reason being, larger the WRE and, larger the value of delta C, okay, you essentially suppress the extent number of PBHs that are formed. And the bottom line is as follows. What you find is that there are different curves that have been plotted here. These evidently don't fit the data very well. This is the secondary gravitational waves. Most of these modes have re-entered during the epoch of reheating. That gives us another parameter to vary as well, omega RE. And you focus on these models, for instance, R4PF, okay, which is the solid red curve which fits the data fairly well. And if you look at the solid one, which corresponds to delta C of AN, or this dash curve, which arises here, this one here, and these red curves fit the data fairly well. And importantly, I'll just highlight this. Importantly, they fit the data with a significantly higher Bayesian factor when compared to those supermassive binary black hole modes. But this is based on the codes that NANO-Grav has provided us, and I understand there are uncertainties associated with it, but given this and given this modeling, what we find is that a secondary gravitational wave spectrum, spectrum of gravitational waves produced during an epoch of reheating with an equation of state which tends to higher values greater than 1/3 seems to fit the data very well. And there are a couple of other points I want to mention here. I indicated that how we ensured that the FPVH is consistent with the current constraints, and that is what you can look at. This guy here, the solid one here, which corresponds to delta C of delta analytical, or delta C of 1.5 times the delta C analytical that I had indicated earlier, the R2PB, right, here, What you find is that this fits the data, this is consistent with the constraints on FPVH, And I had briefly mentioned as to how, if you try to enhance the power on small scales, you can't blindly enhance the power on small scales soon after the CMB data. Remember the CMB data constrains up to about K of 10, 1 megaparsec inverse or so, and there is some large scale structure data and 21 centimeter data thereafter. But there is a stronger Firas constraints from the spectral distortions. How much is the deviation from the thermality of the CMB? And these are the constraints on the primordial power spectrum from the Firas, which is the current constraints, and the projected constraints due to a possible future mission called PIXI. And this kind of spectrum that we have worked with, primordial spectrum, this is the analytical spectrum. Remember, this is the analytical spectrum, and these are for the various best fit parameters, and they are indeed constrained, consistent with the constraints from spectral distortions. So that's the take-home message, that as far as the PTA data is concerned, modes which re-enter during an epoch of reheating seem to fit the data fairly well, significantly better than the gravitational waves and isotropic background of gravitational waves produced by the supermassive black hole binaries. And this is the final result actually. And what we have also done is that for these various values of WRE, we also indicated the primary gravitational waves. And what you find is that some of those WRE, I mentioned that WRE greater than 1/3 is, provides a better fit to the data. But what can happen is that the primary gravitational wave, for some of them close to 1, can either cross LVK or even cross the delta and effective bound that I mentioned towards the end of yesterday's lecture. So essentially what our analysis suggests is that WRE slightly higher than 1/3 is preferred, but we need an extremely small reheating temperature in order to make sure that all these scales, all these frequencies as observed by the NANO-Grav instrument is, re-enters during the epoch of reheating. So I come to the end of my lectures. I'll close with a very broad outlook, and I have some few references, If one of the future CMB missions, such as Lightbird, detect, I should also use this to advertise, we are working towards a possible Indian mission. It's called ECHO, it's called Exploring Cosmic History and Origins. And if one of these future missions detects signatures of primary gravitational waves, which I mentioned is the holy grail in cosmology, it will help us determine the energy scale of inflation. And if you see primordial 2-point functions, and maybe you can see 3-point functions, this is what I had hoped for when BISUB had shown some promise initially. You can arrive at indeed strong constraints on the dynamics during inflation. The observations by LIGO are a culmination of almost 50 years of effort to detect gravitational waves, and they have opened up a new window to observe the universe. The observations by the PTAs and their possible implications for the stochastic background offer a wonderful opportunity to understand the physics operating over a wider range of scales in the universe. Remember, to repeat, the CMB constrains over only a small range of scales. If you have non-trivial dynamics during inflation, during the later stages of inflation, or you have an epoch, elongated epoch of reheating, they will leave telltale signatures on both the primary and the secondary gravitational waves. And if indeed nature operated in this manner, you are going to be able to see them in the forthcoming missions. And of course, forthcoming gravitational wave observatories such as LISA, Einstein Telescope, and Cosmic Explorer can, it will provide us with the unhindered view of the primordial universe. Just a few references, okay? And here are some relatively recent references on primary and secondary gravitational waves. And this review by Dominic discusses in detail the secondary gravitational waves, both during inflation and reheating, which I could not spend enough time deriving or discussing. And here are some work, related to what I have talked about in these two lectures, my own work, with my students, Raghavendra, who's currently a postdoc with Nicola Bartolo, Saha, who was my former postdoc, and Huck was my former postdoc, and Suashish was my former student, and Baumik was my former postdoc. And these papers can complement these references, particularly when I'm talking about specific models, some details related to the algebra. I'll stop there. Thank you very much for your attention.
Well, thank you for your very clear and well laid out lectures. Are there questions for Sriramkumar?
With the last model that you showed to us, you need a very low reheating temperature, which is like at the order of tens of MeVs. So how about the duration of this reheating phase with a rather stiff equation of state?
What is the duration of reheating? Okay, I am not able to you want an estimate in terms of number of E-folds. Okay, I don't have it immediately. I understand. So I should be able to estimate it. I'm not able to say, Christoph, immediately. I'll clarify this. Yeah, it's an interesting question. I didn't think about it. Yeah. So the reason for our reheating, it can be relaxed. Okay, I do not know what its implications are. It is just that if I allow them to enter during reheating, it provides me another parameter to vary to compare with the data. The challenge is trying to estimate this spectrum if reheating occurs in this regime. Then it becomes mathematically challenging to calculate the transfer functions and the script IC and the script IS, etc. So I believe that one can relax the low reheating temperature and carry out this exercise, provided we can calculate the spectrum of secondary GW.
Is there some reason why you want to know specifically about the duration of reheating, or you just want to know what is the temperature at reheating?
I was just wondering if there is any information about the energy scale of inflation, because with a prolonged epoch of reheating, we can have the energy scale of inflation much larger than that of the reheating temperature. So that was I was after.
So what we find is that this constrains, the delta and effective bound constrains that the HI, the energy scale of inflation, or the tensor to scalar ratio equivalently, better than this. Okay, so I need to remember the results now. I find that the R of 10 power minus 3 can be consistent if WRE is not very high, but if it is high, it points to a lower scale of inflation. Yeah.
So I think when you go from the slow roll to ultra slow roll, kind of, it's just engineering a potential, or it's just like some physics wise to one can understand this part?
A simple model, long back there was a model by Anupam Mazumdar and co. These are these MSM models. You had phi squared minus phi cube plus phi 4. Okay, something like that will permit with suitable choices of the coefficients will permit a point, permit a point of inflection. But something I did not mention is that, one of the challenges in single field models, okay, of course, some of these potentials look fairly complex, okay. They're motivated by string theory, so, okay. So, one of the challenges you find is that on large scales, in some of these models, the NS is not very consistent with the data. You'll find that NS deviates at least by 3 sigma or so in single field models. The tensor to scalar ratio you can ensure is consistent with the CMB constraints, okay? But the NS can be significantly different from the CMB suggested value. So the best way you can fine tune, we have constructed scenarios, you can reconstruct scenarios such that it is consistent here and leads to peaks on small scales. But one simple way to circumvent this problem is examine two field models, which is something we have done as well. And you can ensure that the spectrum is very similar in two field models, and it is is very consistent with the CMB data on large scales. So there are many models. So I think it will be unfair to call them as even a simple model like this will lead to an epoch of ultra slow roll inflation. Okay, so it is not, it is easy to achieve. It is challenging to ensure that the spectrum is consistent with the CMB on large scale. So you need to fool around with the parameters, or you will end up having a very prolonged duration of inflation. Okay, but you can consider more non-trivial scenarios or two-field models where these problems don't arise. How natural those models are, I think I will not be able to comment.
So, just a quick comment. So in one of the potentials, you had this polynomial, I think phi squared. Yeah,
this one. That's what I was referring to actually.
Yeah. Yes. So this is the symmetric inflection point model. But you had another slide where you had same polynomial divided by 1 plus beta.
Yes.
Right.
Yes.
So that I can tell you. So not this one. So you had another slide where this one. So the first on this, you can use standard model Higgs non-minimally coupled to Ricci scalar, and you can get exactly same potential. The cubic term will arise from the RG running of the standard model Higgs. So you can play with the top coupling, and people have shown that you could get very similar potential with the running of the RG Higgs, and you can get the same story.
Yeah, this is the Espinosa and others, right?
No, this is not Espinosa. So this was by Garcia-Bellido. So this is called critical Higgs inflation Garcia-Bellido.
Okay.
Right. So I
guess this is the one.
Yeah, this is the one. Yeah, this is the one. So this paper they are using standard model Higgs with a non-minimal coupling, and they are playing with the RG running to get this potential.
So there are, all he's saying, Narendra, is that there are well-motivated models.
So I have a question. So my question is that can you go to the plot of the scalar-induced gravitational waves? I mean,
sorry.
Can you go to
which plot?
Any one of them which shows some detectors and yes, okay. So these are different benchmark points, right? If I understand correctly.
What does that mean by benchmark?
So I mean that the green.
Okay. So actually, this is a bad. I should have used a better figure. Okay, let me go to this one. You're happy with this?
Yes, fine.
Yes.
So these are different benchmark points. So maybe for this.
Which are different benchmark points?
The different colors.
Oh, the different colors correspond to different values of WRE.
Okay, that's fine. Okay, different benchmark, right? So maybe in this paper, I'm not sure whether you looked at the corresponding primordial black hole production, but in general, whenever you have these benchmark points, you have a corresponding estimate for the mass and the fraction of the primordial.
So that's what we had, right? That's what I showed, right? This is the one.
Yes.
So the best fit values for R2PB with dashed and solid lines, blue this one and this one. are consistent with the PBH.
Right. So my question is that whenever such primordial black holes are formed, they will start to merge, right? So do you expect the entire shape of the spectrum, especially
you are talking about an astrophysical source of additional astrophysical source of black holes?
When you see the entire spectrum, you will see the combination of
I agree. I mean, I will see many other things as well, Anish. Okay. Yes. No, we have not calculated. Yes, I agree. So if I need to estimate, there are some people who have done that. We have not done that. Okay. This is just the spectrum. This is just the spectrum. Where is that? This is just the spectrum induced by the scalars. Yes, if you have a reasonable number of PBHs that are formed, they will coalesce and create a spectrum, another secondary, okay, a tertiary spectrum of black holes. Okay, but I do not know where the peaks will lie. They may lie at much smaller frequencies.
So my expectation is that the peak will probably be the same, but
why should the peak be the same? That will depend on the masses of the black holes.
True. But usually they modify the UV part, so they don't
Sorry.
So
they will change here, you mean?
No. UV.
UV yeah. Here. Yes.
A bit more to the left, probably regions here.
Okay, so the LIGO is somewhere here, right?
Yes, so here
LBK is here.
Little bit
so
to the left.
These masses are, okay, I'm going in the wrong direction. These masses are smaller than smaller than solar masses. Okay, so I do not immediately know where they will fall, in which they will go even larger frequencies if I'm right. Okay, I'm not able to comment about that. Where the merging PBHs with these FPBHs, where their gravitational waves will come, astrophysical sources of gravitation.
Thank you.
I'm not able to comment about it.
I have a question about the polarization of secondary gravitational waves. So am I understanding correctly that in your models, the secondary gravitational waves are not polarized?
Yes, we are just working with Einsteinian gravity, and there is no sources that, something I didn't highlight. I have worked in a scenario where there is no violation of parity.
So could you give an example of a scenario in which I might expect the secondary gravitational waves to be polarized? Can I still achieve that using, say, scalar fields as the scalar
you mean, can I have scalar fields sourcing a polarized gravitational waves? Is that?
I guess the question is whether it's a generic expectation that secondary gravitational waves will be unpolarized, or
so
are there
if I
examples
have
in which
helical magnetic fields, for instance, if I have helical magnetic fields, I would imagine they will induce polarized gravitational waves. That is one thing I'm to some extent familiar with. Okay, there is Subhashish Maiti who will talk about it. Okay, that is one source of polarized gravitational waves. Or if there are small violations of parity in your gravitational sector itself during inflation, that can lead to some effects.
Any other questions? Comments? Thoughts? Feelings? Oh, here we go.
So, this is just a quick comment. I mean, we discussed this yesterday, that there was some pushback against the very high base factor you get for your model as opposed to an astrophysical model. I'm wondering if you've also been provided, so the NANO-Grav team have put out an erratum to their new physics paper. It rescales, so they've done similar analysis because we all did that. And it rescales the base factors for the new physics models as well, a little bit. It's not a huge amount, but it rescales by a small amount. So I was wondering if
I wasn't familiar with that. I should look at it. But, the difference is so much, if it's going to change by, even if it goes by a factor of half, it's still substantial.
So, okay, I do find that a bit strong because we have looked at this within the PTA groups and we don't find such a strong difference. But then when we do the analysis, we play a lot of games with the spectrum, because as you show, the spectra from PTAs are currently very, very poorly constraining. And then if you make a choice and you slice it at a certain number of frequency bins, claiming only these bins can effectively contribute because these are the ones which are really constraining, then these base factors do change by a significant amount. And you see this in everyone who's trying to do this, that if you pick and choose, then you can do a lot of things. So I'm not very surprised by it, but I do agree that compared to what the PTA groups are putting out.
NANO-Grav itself had this number.
Yes, but then they had to correct it because,
okay.
But even in the NANO-Grav paper, I don't remember if they're using all 30 frequency bins or if they decided to use the first 9 or the first 12. And then, of course, your base factors do get affected depending on where you're slicing things. So we've seen this happen in the internal releases, and that's what I was slightly reminded of. But also there is an erratum where the NANO-Grav claim is revised slightly downwards. But then for us, where we stand is that we don't really have a huge difference between the astro and the Cosmo background.
So let me make 2 points in that regard. The first concerns the fact that, there was an issue in the literature about overproduction of PBHs. So what we found, what we carried out is an analysis which ensures that it is consistent with the constraints on FPBHs. That is this, okay, simultaneously. So people just, try to fit with the NANO-Grav data. We ensured that. And that points to a higher WRE. That can be the take-home message. This particular thing about the Bayesian evidence, that is what we see. I will not contest you if you say it has to be rescaled. But I would imagine even number like 20 or something, I will go home, go to town with. So if it is 200, I'm excited. So of course, I cannot comment more than what you have.
Okay, I think with that, let's thank Sriramkumar once again.
Thank you.